Primera sesión de este año del Coloquio Interinstitucional de Análisis y sus aplicaciones. Es para mí un verdadero placer presentar al profesor David Damanick de la Universidad de Rice en Houston. Él hizo su doctorado en Alemania. De hecho, tenemos el mismo asesor de doctorado, el profesor Joachim Weidmann. Después se fue a Caltech, trabajó en Caltech varios años y desde 2009 es full profesor en la Universidad de Rice en Houston. Por favor, démosle la bienvenida al profesor David Damanick, que nos va a hablar sobre exponentes de Lyapunov, aplicaciones recientes del teorema de Furstenberg en teoría espectral. Por favor, David.
Thank you very much. So thank you for the invitation. It's a great pleasure and honor to be here. Thank you for coming to the talk. So I will try to make the talk accessible to a general audience. So whenever something is not clear, please ask or stop me and just ask that I explain in more detail. So of course, sometimes I will talk about certain concepts and I'm not sure if you know the definitions, and if I should explain what they are, please again, just let me know. So the talk will be about the phenomenon of Anderson localization. So Anderson localization is a statement about the Anderson model, and the Anderson model was proposed by Anderson in 1958, or rather in 1958 he wrote a paper that explained that randomness can have quantum states. So that trapping property is the phenomenon of Anderson localization. And so this is Anderson localization. And so for this phenomenon that was described in this 1958 paper, he received the Physics Nobel Prize in 1977. And since the 70s, mathematicians have tried to rigorously prove the statement of Anderson localization. And there are several flavors of Anderson localization. We will see two in this lecture. And so this talk uses this concept of Anderson localization as a backdrop, as a motivation, but it will really also talk about the phenomenon itself. But on a technical level, I want to explain why in certain scenarios this theorem of Furstenberg is crucial in these rigorous proofs of Anderson localization. So before we get to that, I want to talk a little bit about the general setting, and then later I will specialize to the case where Furstenberg's theorem is very important. Okay, so the Anderson model, as discussed in the original paper, is a discrete Schrödinger operator on the d-dimensional lattice. You can look at continuum Schrödinger operators, you can replace the lattice by other geometries if you want. You can ask similar questions, but the standard model just is a discrete Schrödinger operator, dimensional lattice. And so I will write down what that is in a moment. But a Schrödinger operator consists of two parts, the Laplace operator and a potential. And that really corresponds in classical mechanics to kinetic energy and potential energy. And so the potential here is random because we are modeling a random medium. Okay, so the potential should be random, and so you generate this random potential by considering independent, identically distributed random variables. So basically at each lattice site, you will have a random variable, and they are independent and identically distributed. So I will actually denote the probability measure that generates the distribution at any given lattice site by nu. So nu is a probability measure on R. And again, if you don't know what a measure is, it's not important. You can think of a coin. You toss a coin that has two outcomes, heads or tails, or 1 and 0. And you toss it, and then you see either 1 or 0, and you write down what you see. And then you do it again and again and again with the same coin. Using the same coin is using an identical distribution, and tossing it sort of again, regardless of what happened before, is the independence in some sense. So yeah, if you think of coin tosses with the same coin that are independent, you have an example of what we're modeling here, but you can use other ways of generating random numbers rather than just tossing a coin that has two outcomes. Okay, so this measure will have points in its support, so basically numbers that are possible according to that measure. And of course, the assumption is that at least two numbers are possible. Because if only one number is possible, you will write down the same number at each location, and that is not random at all. That's just a constant function. That's not random. So to have honest randomness, you need to have at least 2 points, and that's our minimal assumption. But other than that, we don't need much else to write down the model and formulate the expected results. And so again, formally, you toss the coin. So basically, you draw according to this measure nu at each location in ZD. And so formally speaking, you consider this product measure. So this product measure basically is your sense of probability of seeing some collection of numbers, right? So at each location, you generate randomly a number. Once you're done, you have numbers everywhere. And you have many possible outcomes. And outcomes happen with certain probabilities. And this probability that, describes the outcome as a function from ZD to the possible values here is this product measure mu. And so the product measure really says that we're looking at, independent random variables. So that's the reason that we're taking the product here. And this identical distribution is that we take nu every time at each location. Okay, and so omega here is the set of all possible outcomes. So the set of omegas is the set of functions from ZD to the possible values you can place at each site. Okay? And so this omega will really be your potential. So your potential, your random potential, is nothing else but this random function from ZD to the possible values. And that we want to use as the potential of a Schrödinger operator here. Okay, so this is what a discrete Schrödinger operator looks like. So I said it contains 2 parts. This is the discrete Laplace operator. So this is how many people write down the discrete Laplace operator. So basically, if you want to apply the discrete Laplace operator to a function and ask what value it takes at n, you have to look at all the neighbors, right? So if you are in Z2, then the neighbors are here, 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 and here. You have 4 neighbors. And so you look at your function, the values of your function at the neighbors, and you add them all up. That's what happens here. And this sum then is the value of the discrete Laplacian applied to the function psi at n. And the second part, this is sort of this analog of the potential energy, is obtained by just multiplying the value of psi at n by your random potential at n, so which really is nothing but this random number that you generated at location n in ZD. Okay, so this is a way of mapping a function psi to a new function, but really in quantum mechanics you want these mappings from functions to take place in something called a Hilbert space. And so the Hilbert space here will be little L2 of ZD. And so these are all functions from ZD to the complex numbers whose absolute value squared is summable. Okay, so the square summable functions on ZD. So such functions, psi, you put here, and then you form this object. And then by our assumption here, so this is not an essential assumption, but we made it to make things a little easier. So this support of nu, the set of possible values that you can place at a location, will be assumed to be bounded. And so therefore, this function turns out to be bounded, and therefore this whole object here is sort of bounded. And so in other words, as a result, you will then be able to check, if you want, that for every psi in here, the object defined here will also lie in L2. So you really get a map from L2 to L2. So that's what the Schrödinger operator is. Okay, so here's a point where I mentioned before, I don't know if you know the definition, so if you want to be more detailed than I am, just let me know. So I have this way of sending a function in L2 to a new function in L2, and this is actually a linear map. And in fact, it's also self-adjoint. There's a scalar product here in which you can just bring sort of the operator to the other side. And so then, as a consequence, the spectrum of this operator is a subset of the real line. So it's real because the operator is self-adjoint. And what is the spectrum? So if you had a finite matrices here, the spectrum would just be the set of eigenvalues of that matrix. And so if you have these spaces that generalize finite dimensional vector spaces, so this is an infinite dimensional space, you cannot just say that the spectrum should still be the set of eigenvalues because there may not be any eigenvalues. So for example, if V is 0, this is not very random, but of course it's still a potential that you could choose. So if V is 0, then if you just have the discrete Laplace operator, that doesn't have any eigenvalues. But you still want to be able to talk about something that you want to call the spectrum that catches the essential flavor of what the eigenvalues catch in the finite dimensional case. So the spectrum of an infinite dimensional operator is really defined as follows. You take the operator, subtract a number times the identity, okay, h omega minus e times identity, and you ask whether this has an inverse. And if it doesn't, then E is in the spectrum. That's the definition of the spectrum. And so this is a reformulation of what an eigenvalue of a matrix actually is. And so the spectrum, as I said, for this particular operator here will be a subset of the real line. And this is a consequence of the values of the potential being real. Okay? So this is the spectrum. And so then also there is something called the spectral type. So I will not actually need to define this in the usual generality, because what we will talk about is actually the presence of eigenvalues. I just told you that there aren't always eigenvalues, but one formulation of the phenomenon of Anderson localization is that there are many eigenvalues. Okay, so spectral type is, so one aspect of spectral type is the question, are there eigenvalues? And if there aren't eigenvalues, what else is going on? So what we will focus on for these operators is actually the presence of eigenvalues. And for that, we really just need to know what an eigenvalue is. And so I guess that is probably something you've seen before. So the question really is whether I can find non-zero psi's so that h omega psi is equal to some multiple of psi. The multiplier would be the eigenvalue, and psi would be the eigenfunction. And so the question here is whether you can find many eigenvalues and eigenfunctions. Okay, but so this statement here means in this context, for example, that if you take all the eigenvalues of h omega, so h omega certainly depends on which omega you take, right? Because if you have these many realizations of choosing random numbers, you have many different potentials, many different operators, and therefore possibly many different collections of eigenvalues. But there is something that tells you that a certain thing is almost surely preserved. So this is hidden in this funny statement here. And what is preserved is the closure of the set of eigenvalues. Okay, so these eigenvalues will actually lie dense in some set, and that set is the same for almost all omegas. Okay, so I have my notion of probability on the realizations of my random potential. And with probability 1, it will be true that the closure of the set of eigenvalues is always the same set. So that's what's known. That's not too hard to show, actually. And so, oh, sorry, I also didn't tell you that the spectrum, I told you how it's defined, but this almost sure independence also applies to the spectrum. And so the spectrum turns out to be almost surely equal to the set. And the funny thing here is, while the operator is a sum of two operators, the spectrum turns out to be the sum of their spectra. And this is not a typical thing to occur, but it occurs here. So if you just took the Laplace operator in d dimensions, its spectrum would be this interval here. And if you took just this multiplication operator, ignoring this part, just this part, its spectrum almost surely would be the support of the measure nu that you'd use to generate your values. And what is the topological support? The topological support is the smallest closed set whose complement has zero measure. Basically, it's really the closure of the set of values that you can actually place there. Okay, so the spectrum almost surely is known in this case. The eigenvalues are not sort of known, and in particular, they will move around quite a bit. So the eigenvalues themselves will depend very sensitively on omega, but the closure of the set of eigenvalues will be the same. Okay, so here are two versions of Anderson localization. So again, initially I told you the phenomenon of Anderson localization is that if you have a random environment and you look at quantum mechanics, so how states in quantum mechanics evolve over time, Anderson says, well, if the environment is random, then it's possible that these states don't travel. They are localized. They remain where they are and cannot move from here off to infinity, for example. And so this intuitive notion of trapping of states is mathematically often described as dynamical localization because it's about a dynamical process. So in quantum mechanics, there are two equations. There's a time-dependent Schrödinger equation that tells you how things change in time. And there's a time-independent Schrödinger equation that there's no time parameter. And so you can ask related questions, namely whether the solutions of this time-independent equation are localized in space. And this is exactly what spectral localization is about. Okay, so spectral localization is a time-independent notion, and dynamical localization, there is a time parameter involved. And specifically, the two concern the time-dependent and time-independent Schrödinger equation. And I will make this more precise later. But there are those two versions of Anderson localization. And so the spectral localization statement is exactly this statement that talks about eigenvalues. Okay, so spectral localization means that almost surely, and by the way, I should have stressed that before. So if you look at all the realizations of your random potential, the best you can hope for are statements with probability 1. It's not good to expect a statement to be true for all omegas, because if a random feature occurs because of randomness, but not in the absence of randomness, then it cannot hold for all, because some of the omegas will not be random at all. Okay? So because if you keep tossing a coin, it's possible, though extremely unlikely, to get only zeros. That is not a random sequence, but it's certainly a valid outcome of your random experiment. You can produce a constant sequence, and you can also produce a sequence 0, 1, 0, 1, 0, 1, 0, 1. So periodic sequences are possible outcomes, but all these outcomes happen with probability 0. Okay? So if you have a feature that you expect for random environments, but you don't expect for periodic environments, that feature cannot hold for all omegas, because some omegas will not be random, they will be periodic, for example. Okay? So therefore, in this study of random operators, all the results that you prove will have this qualification saying that they hold mu almost surely. So that's really the best you can hope for. And so spectral localization means that H omega has pure point spectrum, I'll say what that is in a second, in a suitable energy region with exponentially decaying eigenvectors. Okay, so let's talk about our eigenvalues and eigenvectors. So let's ignore this part for a second. So pure point spectrum just means the following. So you look at all the eigenvectors of your operators. So again, I'm assuming that we know what an eigenvector is. It's a non-zero psi, so that operator applied to psi is equal to a multiple of psi. So the psi is an eigenvector. So now for our H omegas, we look at the eigenvectors. And pure point spectrum just means that you can find a basis of your space consisting of eigenvectors. So that's what pure point spectrum is. You can find a basis of eigenvectors of your operator in question. Okay, so this funny business with a suitable energy region, you get the statement I just explained after projecting to this energy region. We will not actually make use of that in this talk when we talk about the applications of Fürstenberg's theorem. But just to be precise, you actually have a spectral localization statement only in parts of the spectrum in general. This is, you can find a basis of eigenvectors, that's the pure point aspect. And these eigenvectors are also claimed, if you want to establish spectral localization, to decay exponentially. Okay, so you have an eigenvector, and what you want is that it decays very fast at infinity. And so this is what spectral localization wants to capture. The eigenvectors are localized in finite regions modulo exponentially small errors or tails. That's what spectral localization wants to claim. Okay, dynamic localization, as I said, there is some time parameter. You can see it here. And again, there's this funny spectral projection, which I will not actually go into much. So here, this object here, if you disregard this for a second, says the following. So you're looking at a state, and in fact your state is delta 0, and it's a very simple function on ZD. It's a function that takes the value 1 at the origin and 0 otherwise. That's delta 0. That's certainly an L2 function on ZD. It's square summable. And so the interpretation is that at time 0, with probability 1, you start in the origin. And now you let your quantum mechanical time evolution run. And the quantum mechanical time evolution is exactly given by this funny exponential here. So you have your Schrödinger operator, and if you take e to the minus ith, then this takes you from the initial state to the state at time t. Okay? And so there is some more sophisticated way of defining this, but in our case, it's easier to define. Namely, I explained that h omega is a bounded operator, and for bounded operators, you can define these exponentials really just using the Taylor series of the exponential function. You can plug h omega into the Taylor series of the exponential, or you plug minus I times t times h omega into the Taylor series, and this infinite series will converge. So there's a limit of the partial sums, and that's just what the exponential is. And so this object then, as I said, takes you from the state at time 0, which we choose to put all the mass at the origin, to what you have at time t. So now the question, whether you can move from here to there, is really a question. You start here at time 0, you apply e to the minus ith, and then you ask, does the new function e to the minus ith applied to delta 0 have any sort of mass over here? Because the non-zero entries really tell you the probability of having your state at time t over there. Okay? And so therefore, what you want to show in the dynamical setting is that even if you wait a long time, you don't travel very far. So this is what it means here. Time t remains mostly in some fixed finite region for all times, so that if you start locally, you're confined to some finite box no matter how long you wait. That's the dynamical aspect of being trapped. That's dynamical localization. And that's the original sort of physicist's interpretation of what Anderson localization really should be. But for the longest time, actually, mathematicians have focused on this, but eventually they switched to also a study of that, which is a bit more difficult, but can also be proved. Okay, so now I want to quickly review some of the expected results and some of the known results. And so here you will see, actually, that this funny business with this part of your spectrum is in general necessary, but for the rest of the talk will not play a role anymore. So first of all, there is a dimension dependence. So D1 means that we are on Z. So it's the one-dimensional lattice. And so we are really trying to, for example, move to infinity by being confined to one dimensions. And so here, actually, because dimension is so low, it turns out that you don't need to pass to the subset of the spectrum. So throughout the spectrum, you have the full phenomenon of Anderson localization. Okay, so this is first of all expected, and second of all known. Okay, now in d equal to 2, now we are on Z2, the two-dimensional lattice. It's conjectured the same result. Okay, so also in 2 dimensions, people expect that throughout the spectrum you are localized both for the eigenfunctions and for the time evolution. And it's not known. So basically, the current results are like this. There are some results for d equal to 1. And there are some results that are proved for all dimensions. And so in particular, they don't make a distinction between 3 and 2. Okay, so what is known and conjectured in 3 dimensions? So first of all, it is known that in neighborhoods, oh, wait, sorry, there's a typo. This is supposed to be the boundary of the spectrum, I'm sorry. Okay, so the spectrum, remember, is the sum of an interval of length 4D and the support of the random distribution. And if you think about what kind of sums you will get a finite union of intervals. So this almost spectrum will be a finite union of intervals. And so here I'm talking about the endpoints of these intervals. Okay, so you have finite union of intervals. Each of these intervals has 2 endpoints. And each of the endpoints has a neighborhood in the spectrum on which these results are true and known. So that's what the first sentence says. But these results make no statements outside of these neighborhoods of the endpoints of these intervals. And however, it's conjectured in dimensions 3 or higher that eventually a localization doesn't hold anymore if you move away from the boundary points too much. So in particular, localization doesn't hold throughout the spectrum if the randomness is not too large. So that's a very, very big conjecture. So it's sometimes runs under the name delocalized states or Anderson delocalization. So basically, it's just a claim that you don't have localized eigenvalues in the sense that there are no eigenvectors, and in particular, no exponentially decaying eigenvectors for E's far away from the endpoints of the spectrum. Okay, so this is what's conjectured. It's wide open. People really have no idea how to prove it. But you see here that in terms of the conjectured results, there's a difference between D equal to 2 and D equal to 3. Namely, here you have localization throughout the spectrum, and here in parts of the spectrum. And so you have localization in parts of the spectrum, and that's the result that's known in 2 dimensions, and not the conjecture. Throughout the entire spectrum, you localized. So that's basically the status quo of Anderson localization. And so the next slide will talk about some results and some major contributions to this story. So here's just an overview of what's known. The next slides will just talk about specific results and specific authors of results. And so the rest of the talk eventually will actually be about the one-dimensional case. This is the case where Fürstenberg's theorem is really important. And so that is what I will then focus on. And you see in one dimension, you don't need to introduce the set sigma L, which is the localized region, because the full spectrum is the set in question. Okay, so right, so this will be a long list of papers, but let me explain why I'm listing these. So the goal of the talk will be to explain recent work that uses Fürstenberg theorem to prove the phenomenon of Anderson localization in certain settings. And there are actually several results that fit this bill. And the first paper we finished in 2017, and that was a new proof of the known one-dimensional result. So proving in one dimension Anderson localization. So you will see in this list, the first proof was given in 1987. But the proof was very difficult. And so with my students and postdocs, we tried to find a simpler proof. And so that's one of the things. But once we had that simpler proof, new problems all of a sudden became accessible because the previous complicated proof couldn't be carried out, or people didn't at least carry it out for these other problems. But our new proof that's much simpler actually can be carried out in this new settings, and therefore then we can obtain new results. So the remainder of the talk will first talk a little bit about our new proof of the known result, and then give you a new result that can be obtained with these ideas that were developed in this new proof. Okay, and so basically I want to aim for that story. All right, so the first mathematical localization result is from 1977. It's by Goldscheid, Molchanov, and Pastur. And they proved Anderson localization not for the model I introduced here, but for a continuum model. And the reason why they considered that, there is a heuristic or philosophy that says the more randomness you have, the easier it is to prove localization. That is sort of convincing on heuristic grounds, but also if you look at the proofs, it's also actually true. Many of the proofs that establish localization, if they work for some version of randomness, if you increase randomness, they still work. Okay, so this is some sort of monotonicity in the level of difficulty. So if you lower randomness, the proofs should become more difficult. And so this continuum model just has more randomness than our model because our random model has one random variable per lattice side. And the continuum model, so basically they use Brownian motion, so you have a continuum of random decisions. There's just more randomness present, which intuitively could make localization proofs easier, and I mean, it probably did make that proof easier. Okay, so I listed because it was the first localization proof, but it's not the first result for the model introduced on the first slide. That belongs to Kunz and Tsuya from 1980. So they proved localization in the case D equal to 1, so one-dimensional on Z, for absolutely continuous news. So I gave you this example where you toss a coin. So this is easy to visualize or to envision, but this is the hardest to study. So when I talk about monotonicity and the randomness, having a coin, this is the least possible the model with the least amount of randomness, because you only have two outcomes. The more outcomes you have, the more randomness you have, because, I mean, in terms of entropy, I don't know how you want to think of these things, there's just more uncertainty about the outcome of the process of, evaluating your coin. And so an absolutely continuous nu just means that if you want to determine the probability of an outcome, so basically you have to look at intervals, and then you have to integrate the density over the interval to generate the probability of having a value in that interval. And so this certainly is a reasonable choice for a random variable, but certainly does not contain this coin toss example. But the absolute continuity of nu is absolutely crucial to their proof. Nevertheless, their proof is very nice, and it was the first localization proof for the honest Anderson model. Then in 1983, Fröhlich and Spencer developed a version of multiscale analysis, which is an inductive procedure to prove statements inductively along a sequence of scales with the intent of proving Anderson localization. This works in all dimensions, and then in 85 was used, multiscale analysis was used to prove spectral localization in all dimensions, and again for absolutely continuous nu. By the way, because I emphasize spectral localization here, Kun Tsu Ya proved both spectral and dynamical localization here. So this first proof in higher dimensions was initially a proof of spectral localization, but also used absolute continuity of your nu that generates your value at any given site in the proof. Okay, and so here's the first result that works for the coin toss. This is Carmona, Klein, Martinelli, 1987. So they look at the one-dimensional case and look at general news in the context in which we define things, including the coin toss example. And they also used multiscale analysis. Okay, so a multiscale analysis at this point was really a very important tool. And in 93, Eisenman and Molchanov, they developed a new approach to localization in arbitrary dimensions, again needing absolute continuity of nu. So the advantage here is that the proof is easier. So this proof of localization via multiscale analysis is quite complicated, and this is a much easier proof. Also, the dynamical localization that you can establish here will be stronger than the dynamical localization that you could eventually establish using multiscale analysis by a little bit. Okay, so there are some advantages here. But multiscale analysis has a very important advantage. So this approach absolutely needs absolute continuity, whereas the absolute continuity here was used in the proof, but it was not clear whether it's necessary. And already here you could see that multiscale analysis, at least in one dimension, could be carried out without absolute continuity. This will never work without absolute continuity, and this one does in one dimension and could in higher dimensions. And by the way, it's not on the list here. It's actually a result of Bourgain and Koenig from, I forget, 2005 maybe, that a multiscale in higher dimensions also works for singular distributions. So eventually people understood that this really was just an artifact of the proof, not of the method. Okay, so up to this point we had localization in higher dimensions for absolutely continuous nu and in one dimension for general nu. Okay, but the proof here for general nu used multiscale analysis, which is quite heavy. And so now I'm actually switching to different models that I didn't define, but I want to mention the paper because it gives the key to our new proof. So Bourgain and Goldstein in 2000, they proved localization for some other type of operators, not random potentials, but quasi-periodic potentials. Okay, but the point is that they proved the same results, and they used a certain method. And so once you see how they prove localization, there is a natural question that you can ask, namely, can I prove localization for random potentials using their ideas? And so this is exactly the motivation for the work that we did. And so there was a follow-up paper shortly after this one that did the same thing, again, via large deviations, for the doubling map, which is another type of potential. But I'm listing it here because the doubling map is closer to random than the quasi-periodic case. But this paper was important because it introduced this new approach to localization via large deviations of the quantity we'll talk about in a second. And this next paper showed how to implement this proof for a model that's very similar to random potentials. Okay, and so this is then finally the 2017 paper that I mentioned before with my students and postdocs. So this is really, this was my research group at the time, so they're all gone by now, but anyway. So we looked at this result here, proved it again, but really in the spirit of Bogin, Goldstein, and Schlack, using large deviations of the Lyapunov exponent. Okay, so and we already then proved a result for orthogonal polynomials on the unit circle, just to indicate that one can also prove new results with these ideas, not only this known result here. And then finally, if I get to it, I hope I will sketch it at least, there's some recent work with Sukhtayev and Filman and Sukhtayev on trees. So there's a community of spectral theorists who study operators on trees. And so there's a family of problems in this area that reduce to things that are very similar to what we studied there. And so there we could then also prove Anderson localization. And this is an instance where we could solve a problem that actually was open before because they didn't have a multiscale analysis or didn't want to develop one for the models that happened here. However, what we do here applies in these settings. So that's basically the outline of the history, and I hope to have made clear what the talk is about. I will briefly explain what the ideas behind this new proof of this result, which is localization in one dimension for general news. Okay, so that's what the topic is. No questions? I will show those. So here are the main results. So as I said, we look at one dimension. So now we're in L2 of z to the 1, so just z. The discrete Laplacian now takes this form, sum of the values at the neighboring sites. So the sites neighboring n are n plus 1 and n minus 1. And the potential is just multiplication by your random function, as introduced before, but now specialized to the case d equal to 1. And v omega is given by independent, identically distributed random variables. Okay. So here is the spectral localization result. So with probability 1, so for mu almost every omega, h omega has a basis of eigenvectors that decay exponentially. That's the first theorem. And this dynamical localization theorem is, as we discussed before, a statement about e to the minus ith applied to some initial state. And then the statement that if you start at m, then you have very little probability far away from it. And so this is basically what the statement is. So if you start at m, then if you look far away so that n minus m is large, then no matter how long you wait, this will be exponentially small in the distance between n and m. However, this exponential smallness, while it always appears with the same decay rate here, the constant in front of it will actually have to depend on the m you start with. This is sometimes called semi-uniform dynamical localization. So it's not uniform because there is an m dependence, but it's semi-uniform because at least the decay rate is uniform. But this is the notion of dynamical localization that can be proved here. So again, this constant gamma is just uniform, but the c depends on omega, gamma, and epsilon, and this prefactor depends on epsilon and m. Okay, so those are the two results. And so now let me talk a little bit about the techniques. So I will get a little more technical now, and so I was going to show you one short proof, but maybe I will actually skip that in the interest of time. But still, now I actually want to make a few definitions so that we know what we're talking about. So the difference equation associated with our operator is nothing but the eigenvalue equation, but in a generalized sense. Okay, so on the left, you really have the operator from before, so let me show it. Right, the operator looks like this, but I've replaced psi, I have replaced a psi by u to emphasize that here psi is a member of L2 of z, and here u is not required to lie in L2 of z. So u is just a general function from z to, say, r or z, or c. Okay, so we're looking at this just as a difference equation, but apart from that, it's the eigenvalue equation for our operator. So specifically, this means that if we look at this difference equation and can find a solution u that lies in L2, then we have found an eigenvector, right? Because our operator is defined in L2, and the corresponding e is the eigenvalue. Okay? So to find eigenvectors, you look at all solutions, and then if you find an L2 solution, you have found an eigenvector. That's the philosophy. And so as a difference equation, that's the thing. Once you drop the assumption of square summability, all of a sudden you can be assured that there are solutions. This is just a linear second-order difference equation, and of course it has solutions. And the set of all solutions forms a two-dimensional vector space. Okay? So because if you prescribe two consecutive values, you can compute all others from the equation. So that's why it's two-dimensional. And so, for example, you could fix the values at 0 and -1. That determines all u's, and in particular, it would determine the values at n and n-1. And not only does this 2 vector determine this 2 vector, it does so in a linear way. Okay, so there's a linear map from here to here, and this linear map is denoted by n and e omega. Okay, so omega is here, e is here, and n is just how far you go, namely from 0 to n. So this is the so-called transfer matrix. It maps pairs of solution entries from one place to another, so specifically from 0 to n. Okay, so I will not actually dwell on this too much, but so what we want to do is the following. So we have this matrix. Because we send 2 vectors to 2 vectors, it will be a 2x2 matrix. And actually, you can check that it's a determinant 1 2x2 matrix. So if E is real here, we are dealing with an SL2R matrix. 2x2 real matrix with determinant 1. Okay, so those are the matrices that participate here. And so what we want to do is we want to look at the size of the matrix. So there's a way of looking at the norm of a matrix. I don't know if you've looked at norms of matrices before. The thing is here, you can take any norm of the matrix. Usually use the operator norm. If you don't know what the operator norm is, then maybe take the absolute value of all the entries and add them up, or take the square root of the sums of the absolute value squares, or any norm on this matrix here will be okay. And so we want to ask how the norm, the size of the matrix, grows as n grows. So we want to send n to infinity. And so this explanation here, which I will not get into, you need a little bit of ergodic theory to verify that, tells you that this rate of growth will actually occur in the same way for almost all omegas. So this is this, well, wonder of ergodic theory that many things happen with probability 1. So this is a consequence of the so-called subadditive ergodic theorem. So namely, there is this number, L of E, which is either 0 or positive, that describes the rate of exponential growth of these norms for almost all omegas as n goes to infinity. So in other words, for almost all omegas, the norm of m n e omega behaves like e to the n times L of E. That's what L of E is. It's sort of the constant you put in front of n in the exponential. So it's an exponential growth with rate L of E, both in forward and backward direction. So you can also send n to negative infinity, you get the same answer. So this number here is called the Lyapunov exponent, the rate of exponential growth of the matrix that maps the values of solutions of this equation from 0 to n as n goes to infinity. That's what the Lyapunov exponent is. And so you see here that it's important to have a one-dimensional problem. So this is the difference equation associated with the operator has a finite dimensional, two-dimensional solution space. If you did the same thing in higher dimensions, it doesn't have a finite dimensional solution space. Therefore, the solutions cannot be expressed like here in terms of finite matrices. And therefore, there is no such thing as Lyapunov exponents. You could look at directions, so there are directional Lyapunov exponents, but you cannot have one sort of matrix that captures everything because that would restrict the dimensionality of what's going on, and it's easy to see that the dimensionality is infinite. Okay, so the existence of the Lyapunov exponent is something that you can only have in one dimension, but in one dimension you have it, and then the question is it useful? Okay. So, so remember that spectral localization is the statement that you have L2 solutions that actually decay exponentially. And so the goal is to show that there are exponentially decaying solutions here. Okay, so then this is a linear algebra exercise if you want. So if you have an exponentially decaying solution here, And so U0, 1 will be some fixed vector, and it's mapped to this exponentially decaying vector. This implies that the norm of this matrix has to grow exponentially. Right? If you start with something large, to make it small, the norm has to be large, because if it wasn't, then it couldn't lower the size that much. So in other words, exponential growth of the norms is a necessary condition for the existence of exponentially decaying eigenvectors. Okay? Because our goal is to find exponentially decaying eigenvectors, we absolutely need exponential growth for the transfer matrices, which means that L of E is strictly bigger than 0. Okay? So that's the first step in the analysis, to show that L of E is strictly bigger than 0. Okay, and so this is the point of Fürstenberg's theorem. Fürstenberg's theorem is a tool that you can use to show that L of E is strictly bigger than 0, the first step in the localization proof. Okay, so how does Fürstenberg's theorem work? So you have your nu, which tells you how to randomly generate x's. Okay, so if you have a coin, then x can take the values 0 and 1. If you have a more general nu, then x will run through the values in the supportive nu. Okay, and so now what we want to do, instead of these random numbers x, I want to look at random matrices. So I fix E, I choose a random number x, form this matrix, and then I regard this matrix as a random matrix. Okay, it's a random matrix because one entry is random. Okay, but that's what Fürstenberg's theorem does. It talks about not measures on R, but measures on matrix groups. In this case, SL2R. So this is why it's a technical term. So nu E will be a push forward of nu, which is a probability distribution on the x's. And now the nu E will now be the resulting probability distribution on these matrices. All of a sudden, you have an E-dependent measure on SL2R. Okay. And so now with that, you form the smallest closed subgroup of SL2R that contains all the possible matrices that you can get in this way. Okay? So you take all the x's in the support of nu, then you get all the matrices that you collect here. And then this will, in general, of course, not be a subgroup. So what you do is you add inverses and all products. Now you have a subgroup. But this will, in general, be not a closed subgroup, so you take the closure. Okay? So you take all the matrices that you can get here, form inverses, form products, take closures, and that's GE. It's a closed subgroup of SL2R. Okay. So now, remember, the goal is to show that L of E is positive, and there are sufficient conditions for that in terms of this subgroup. Okay, so this is what a very special case of Fürstenberg's theorem will tell you. If you want to show L of E strictly bigger than 0, you can arrange for that by verifying condition 1 and condition 2. Condition 1 says that GE is not compact. Well, it's already defined to be closed, so really you have to show that it's unbounded. So the matrices that you start with initially are bounded because I took a bounded distribution on X. So each of these matrices, the collection of these matrices initially are bounded. But once you start taking products, absolutely it's possible for the size to grow. Okay, and so to verify 1, you have to show that you can generate growth of norms by forming these inverses and products. That's the first step. The second step is it's what's called G of E is strongly irreducible. And that means the following. So if you have a M, then of M describe a map from R2 to R2. Okay? So it's a linear map from R2 to R2, and its determinant is 1. Okay, so here's R2. So if you have a vector, then it's maybe sent to some other vector. Okay, so far so good. But then if you take a multiple of that vector, like 2 times that vector, of course by linearity it's sent to 2 times that vector. If you take negative 1/2 that vector, it's sent to negative 1/2 that vector, by linearity again. So in other words, if you take any vector in this line, the image will be contained in this line. Okay? So far so good. And now, this object, PR1, is the collection of all lines in R2 through the origin. And what I've just explained is that M can also be viewed as a map from a line through the origin to a line through the origin. Okay? So M not only is a map from R2 to R2, but also a map from the lines of the origin to the lines of the origin, which is called PR1, real projective line. And so strongly irreducible means that there is no finite set of lines through the origin that's invariant under all elements of GE. Okay? GE is a collection of matrices. The bad situation is if you find finitely many lines, so that any matrix in GE would send this set of lines to itself. That's bad. If that doesn't occur, you have verified condition 2. And once you have verified condition 1 and 2, you can conclude that L of E is positive. Okay. So now there is a condition which is often easier to check than those two. So basically, if you can find two elements in GE that have non-zero trace and their commutator has non-zero determinant, if you find those two, you can verify that 1 and 2 will hold. Okay? So this is something that's very direct. So for example, if we start with these matrices, most traces will actually be non-zero except if E is exactly equal to the X in question. So anyway, so in concrete settings, it's often very easy and direct to check these. However, so for the Anderson model on Z, the next slide, which I wanted to discuss in detail, but I will skip it, will verify 1 and 2 for every E, and so 3 cannot be verified for every E, okay? So it's something that's easier to check, but the scope of applicability may be smaller. So to get optimal results, you really should try to see when 1 and 2 hold. But sometimes if you're just aiming for a quick verification of Furstenberg for many E's, then 3 is very useful. Okay, so the next slide, I will not discuss it in detail, but you will see that the proof is not long. We'll look at exactly this setting here and prove 1 and 2. And so let me just show you what the proof looks like. But I unfortunately am soon running out of time. Okay, so this is the full proof of 1 and 2. And if anyone is interested, I mean, this is in our paper anyway. It's one slide, but again, it would take me 5 or more minutes to explain that. But it does, it does verify 1 and 2. Okay, so, and it works for any E. E is arbitrary here. So in the one-dimensional Anderson model, for any nu, L of E will be strictly positive. And that's the starting point of localization. And so then I said Bogin-Goldstein suggested proving localization using large deviation estimates for the Lyapunov exponent. So let me show you what that is. So we have established positivity of L of E, but that means that in the limit we have exponential largeness, but we only know that after sending n to infinity. But if you want to estimate the solutions of the equation to show that they are exponentially small, you actually need quantitative statements for finite n before sending n to infinity. So this is what these large deviation estimates are about. You know in the limit you're exponentially large, but what can you say for finite n? And so this is an estimate of this type. So L of E will be positive, and 1 over n log of norm of MNE, we know converges to this as n goes to infinity, but how far away is it for a given n? Okay? And so this large deviation estimate tells you if you want to be closer than epsilon, you can arrange that by choosing n sufficiently large. Okay? So basically, being bigger than epsilon is a small probability event, which means with large probability, you're within epsilon. And so this is sort of a type of result that was proposed by Bogin-Goldstein in the context of quasi-periodic potentials, and then for the doubling map. And so we used, in our proof, basically large deviation estimates of this type to prove localization. Okay, and so this is a relatively elementary approach to localization. And again, I will skip the explanation why one is actually almost done. Okay, so at this point, so I will not explain the details here. The goal was to show that the solutions of the difference equation are exponentially decaying. There is an equation, it's really Green's formula, that relates a U of n to values on the boundary of some interval and the Green's function of that interval. And so if you want to show that this is exponentially small, you want to show that this is not too large, and this is exponentially small. And this is exponentially small because you can express it in terms of determinants. And very quickly, these determinants show up in the transfer matrices, and the large deviation estimates told you that the transfer matrices are very large. Okay? So this tells you that you have good control over these determinants. This tells you that Cramer's rule allows you to control the Green's function. Once you can control the Green's function, you can control the solutions. I know it was fast, but just to give you a sense of what sort of the players are in this argument. And so in my remaining very few minutes, I just want to talk briefly about the other model. So these are the more recent papers where we also ask ourselves if we can prove Anderson localization. And so the question is, why weren't these results known, and why can we now prove them? Okay, so in order to explain that, let's look at this picture here. So what we're doing is we're generating trees. So I guess you know what a tree is. So here you have a root. In this case, it has one descendant or one child. And then this vertex here has two children. This vertex also has two children. And this vertex has three children. So basically, you're generating a tree by just telling how many descendants you have for each vertex in your tree. And so I'm talking about random radial trees. Where do you see the randomness and the radiality here? The radiality is the following. So if I have, this is the ancestor of all, and this is, say, the first generation, and this is the second generation here. So you see in the second generation, you have two vertices. And a radial tree requires you to take the same number of descendants for each element in that generation. So in other words, because I have two elements in the second generation, the number of children they have has to be the same for all. Okay, so it's 2 and 2. And then in generation 3, it has to be the same, and it's 3, 3, 3. And the randomness is just in choosing these numbers. So here, one child, two children, three children. So 1, 2, 2, 3. So these numbers, B1, 2, 3, 4, 5, are generated randomly. Okay, so this is how we generate radial trees using random branching numbers. Is that clear? Okay. So the thing is, if you do that, the branching numbers, of course, have to be positive integers. And if you choose them randomly, it's like a coin toss. Choosing a branching number you cannot do with an absolutely continuous measure, right? The distribution has to be discrete. And as I've tried to explain before, many localization proofs work very well for absolutely continuous choices of random numbers, but the case of discrete choices of random numbers causes really difficulties in the proofs in all dimensions, including one dimension. And so this is why there were no results for these random radial trees, because branching numbers have to be integers, and therefore you need a method that can treat discrete and absolutely not absolutely continuous distributions. Okay, so this is philosophically why this is now opened up to our investigation, because we have this new proof that can deal with these distributions. And so we generate these rooted radial random trees. So we take random branching numbers. We can even include potentials. And we can even choose random hopping terms for the operators. And then we define operators like this. So U tilde V just means they are adjacent, so vertices that share an edge. So you could have random hopping between vertices, or you could have a random potential. And the tree, the underlying tree, is random. Okay, so random branching, random potential, and random hopping. And so we treat these two operators. We don't treat the operator that has all three random, but rather only either random branching and random hopping, or random branching and random potential. We know how to do the full case, but that would require certain methods that haven't been published yet. So with the thing that I told you about before, you can only study two random things at a time, not all three of them, unfortunately. Okay, these are the operators on random trees. And then our theorem really is, for these random operators, we have Anderson localization, both in the spectral and in the dynamical sense, as before. And so, again, with my -2 minutes that I have left, let me just show you just one step so that you see how it relates to what we discussed before. So this looks terrible, but let me still give you the main message. So you have an operator, right? This is the random hopping operator, adjacency, that's why it's A. And there's a way of conjugating the operator to make it more accessible. Okay, so you can conjugate by a unitary map, and what you get is a direct sum of operators of some different kind. You get many of them, but each of them is simple. So each of them looks like this. It's a semi-infinite matrix where only 2 diagonals are non-zero, and on these diagonals you have the random parameters in question, right? The b's are the branching numbers, and the p's are the hopping terms. Okay, so this is a special instance of a Jacobi matrix, and these funny things you can study in a similar way as the operator I studied before. Okay, so what we've discussed up to this point allows you to study these guys. You prove Anderson localization for each of them in some quantitative way, and then you piece things together, and then you get it for A. And for the other operator, it's a similar thing. So if you do a random potential, this is S for random Schrödinger, you also can unitarily conjugate it to a sum of many, many Jacobi matrices in which the random parameters show up. And then you can analyze those, and then you prove Anderson localization. Okay? So you see here, the parameters are random, but because the parameters are independent, you will see that the entries here in the Jacobi matrix are also independent. So the thing is, if you were to include random branching, random hopping, and random potential, all of a sudden the resulting Jacobi matrices would not have independent entries anymore. And then you need a way of studying localization for operators with correlated entries. And again, the necessary toolbox exists in abstract space, but not in the published literature. So there's a paper in preparation that will do that. And then you could study the most general tree case. Okay, so this is the recent application of this new approach to localization based on Fürstenberg's theorem proving positive Lyapunov exponents and large deviation estimates for the Lyapunov exponent. And with this, I finish, and thank you again for coming here.